Okay, here is another test question. Spoiler alert: boring problems are boring. So I like to put a little twist in them. I like to, explore things in a little bit different way, and sometimes that makes the problems more difficult, but it also, I think, makes them more interesting. And I like interesting problems. I think they're fun. So here is the problem that we have right here. I have the International Space Station. Okay. And that, let's say it's this one right here. This is the International Space Station. And it's orbiting the Earth at an altitude of 400 kilometers. So that's H right there. And that is true. It does do that. At this height, it travels with a speed of 7670 meters per second. That's also true. So let's just put 400 kilometers. And you could calculate this stuff, but I did it for you. 7670 meters per second. Okay, so that's that. Done. Now, suppose I have another spacecraft over here, and it could be anywhere in the orbit, but I want it to be at the same altitude, but I want it to go faster. So I'm going to need a thruster to do this. So what direction would the thruster need to be, and what would the value need to be? That's what we're going to do. I know you're thinking, well, that's pretty awesome. Okay, so let's look at the International Space Station first, and let's call this, I know I put it in terms of altitude, but let's just call this R1, and that's also R1. So for this space station, I have one force acting on it, and that's the gravitational force. So at this position, even if I call this the X and the Y direction, then I can say F net X is going to be equal to this gravitational force. And so the gravitational force on an object, the interaction between an object and the Earth, the magnitude of that is going to be Fg, that's a G, G, M of the object, mass of the Earth, over R1 squared, where that's the distance between their centers. That's just the scalar value of it. But that force is pointing in the negative x direction. So this, I'm going to write this as negative G, mass of the space station, mass of the Earth, over R1 squared. Now that's going to equal mass times acceleration. So there's the mass, and the acceleration is the acceleration of an object moving in a circle. So that's going to be, I'm going to call that V1 squared over R. V squared over R is the acceleration for an object moving in a circle. AC equals V squared over R. Okay, so there I have that. This cancels. Okay, and I could solve for V1 if I wanted to, but I already gave that to you, right? So that's how I got that V1, and that's the space station. That's all cool. Okay, let's go back over here. In order to do the same thing, I'm going to need, if I'm moving faster, if V1's faster, then this relationship doesn't work anymore for that radius. I'm going to have a different force, right? Because I know this one is, I'll put it right there, 7,600. Okay, so that's not going to work. So let's just pick, for this spacecraft, I'm going to need an extra force. Now, am I going to need that force pushing this way or that way? I'm moving at a constant speed, so I shouldn't be speeding up or slowing down. It shouldn't be this in the direction of motion. It has to be this way, okay, or that way. I'm just going to pick this way, and if I'm wrong, we'll figure that out. So this one, let's say I have FG that way, and I also have FT, which is the thrust, and I'm drawing those in the X direction. Oh, technically that's negative 2. That's in the negative X direction. So if I do that, I can write, for my spacecraft, I have F net equals Ft plus Fg equals mv2 squared over R1, where I know R1, and I know V2, and I know the mass. And I want to solve for Ft. So let's just subtract Fg from both sides, and I get Ft equals mv2 squared over R1 minus G m of the Earth over R1 squared. So that's it. Okay, all I need to do is put it on my values, which I actually know. So let's say Ft. I picked this direction. If I picked wrong, I'll get a negative number for here. So Ft is going to be, I gave the mass of 1,000. V2 I said was 10,000 squared R1 is going to be the radius of the Earth plus the 400 kilometers. So that's going to be equal to 6.471 times 10 to the 6th plus 400 kilometers, which is 400 times 10 to the 3rd. So be careful with this. Okay, I see a lot of people making mistakes with that. Minus g, which is 6.67 times 10 to the negative 11th. I'm afraid I'm going to run out of room. I am. 1,000. The mass of the Earth is 5.972 times 10 to the 24th. And then I need to divide by this same thing down here, 6.471 times 10 to the 6th plus 400 times 10 to the 3rd, all of that squared. Okay, so that's a lot to enter in right there. This is going to be a great chance for you to practice your calculator skills. I'm going to do it with my RPN calculator because that's what I like to do. And you can see how to do this. So there is RPN calculator apps on the phone if you want to use that. Good luck trying to find an actual RPN calculator. This is from 1989 or something like that. I promise you that is true. Okay, so I'm just going to enter this in up here, and I'm not going to take shortcuts. 1,000, enter, 10,000, 1, 0, 1, 2, 3, enter, and then I need to square this. So it's going to be squared. And then I'm going to multiply them together. Now I need to find this thing down here. So it's 6.471 times 10 to the 6th, enter. This one, 400 times 10 to the 3rd, plus. Now I have that right there. I can divide my stuff up there by the stuff down there, divide. So this is my number right here. I don't need to write it down because it's in my calculator. Okay, I don't need to do that, but you could. Now I'm going to go over here. I'm going to include the minus sign with this. I'm going to say 6.67 times 10 to the negative 11th, change sign, 11, enter, 1,000 times. This is the mass of the Earth, 5.972 times 10 to the 24th times. Now I need to find this. That is squared. I cut the squared off. Okay, so it's going to be 6.471 times 10 to the 6th, enter, 400 times 10 to the 3rd, plus, okay, so now I have that, I can square it. Now I can divide, okay, now I can subtract, and I get the following, 6116.6 newtons. That's the magnitude of the thrust, and I was right with the direction because it's a positive number. And there you go. So I'm going to say I withdrew the F thrust. All right, cool.